Hello, it's the boring old git again. Today we're talking about an HP9000 Model 332 workstation. I apologise for noise outside, but we're in a heat wave and I've got the windows open. If you hear any noise, that's the reason. I thought I'd start with just a quick review of what led up to the HP9000 series. Back in 1976, Hewlett-Packard launched the Model 9825 desktop calculator, which was designed to work with GPIB-based instruments. It used their own variant of BASIC called HPL and used a single-line alphanumeric display with a built-in printer and a 1/4-inch cassette drive. If you want to see a good series of videos about the 9825, look at Curious Mark. He did a repair of such an instrument. He has a soft spot for them. I first used one of these when I was at university, and it was my introduction to Hewlett-Packard equipment. The 9825 went through a couple of variations. There was the 9835, which introduced a CRT display instead of the single-line alphanumeric LED display. And then the 9845, which was an enhanced dual processor version, which had dual tape drives and a printer. I say a printer, it has a larger printer than the thermal unit on the 9825. Following on from that, in the early 80s they launched the HP85, which was a much smaller, luggable computer. Again, it could be used for instrument control, and as I recall found popularity in production test setups and small testing setups in the lab. Again, this went through a number of iterations through the life, notably gaining an external CRT and then a much larger internal CRT giving 80 columns. The HP85 series was also based on a custom HP processor system. The next stage in the evolution was the 9836 with 5 1/4-inch floppy drives instead of the tape drive, and the 9816, which came with no storage installed at all other than ROM cards. They're both 68000 based machines with a 100-pin card edge connector for expansion boards. A variety of expansion boards were available, from serial adapters through to networking adapters, SCSI, digital I/O, networking, plus a selection of ROM boards and additional memory boards. These became known as the HP9000 200 series. This led into a number of other 68000 based units in standalone cases with separate monitors, keyboard and storage. And so we get onto the HP9000 Series 300. The first units were launched around 1984 with a 68000 processor. Later units moved on to the 68020, the 68030 and then the 68040. The Model 332 that I've got was launched in 1987. It's based on the 68030, but it is the poverty spec machine of the range, designed really for instrument control rather than workstation operations such as CAD or system debug. The model I have is almost the lowest in the range. It has 2 meg of RAM instead of 1 meg. But it only has the lowest level monochrome graphics, which is 512 by 400. It still has the 100-pin expansion bus architecture from the Series 200, so you can use Series 200 cards in it. It represents probably the last generation of technical computers specifically designed for instrument control. Past the 68040, the Intel architecture caught up with the 68000 and was starting to overtake it. And with the explosion in the use of PCs and PC compatibles, it was more cost effective to use PCs for instrument control than dedicated specially designed workstations. So the Series 300 was really the end of the line that started with the 9825. I picked up the unit for, I think it was £125, so what's that, 140, 150 euros, dollars thereabouts. I think the unit has come from the military. It's dated 1987 and there are stickers up to 2013 on it. I think it was part of the ground support systems for the Tornado fighter. This entered service in the late 80s and was finally decommissioned in 2019. Shortly after, there were a whole selection of HP9000 related items appearing in auctions and on eBay. The unit itself is best described as somewhat tired. It's very scruffy outside, it's certainly seen a lot of action. Worst part is that while there are no major scuffs and damage to the case, no dents, it's very dirty and the front right hand side, the plastic is broken. So I'll need to get some plastic weld on that. So let's start taking it apart. To take the cover off, you have to remove the little panel at the back that covers the main socket and the voltage selector switch. This has got two captive screws and the whole thing just shows the build quality that Hewlett-Packard is famous for. Pulling the case back and lifting it up, and ooh, I think it's clear that this thing has probably been running for 30 years or more and has probably never been cleaned out. It's pretty gunky and horrible in there. I think that is going to need a major clean. What it does show is the way the cooling works. The two fans pull air in through the front grille and fire it out the back. So unlike a lot of PCs where the air is taken in through the fans at the back, it's the other way round. The nice thing with this is if you've got the keyboard in front of the unit, you don't get a cold draft on your hands. So here I'm trying to pop off the front cover. The manual says to insert a screwdriver at about 45 degrees. I'm not having a lot of luck there, so I go in through the back, carefully trying to avoid breaking anything given the state of the front cover. Am I going to get it this time? Is it? Yes, there we go. We can pop it off. And there you see the cooling fans. The large one is for the main system. The small one is for the power supply. And yes, even more crud and corrosion. So a brief interruption to your viewing enjoyment. Before I started reassembling the unit, I checked the fans. The bearings seemed good, but they did seem a little tight. So it was time to fill them with a bit of silicone lubricant. This soaks into the bearings, softens any hardened grease that there is, and then provides a bit of extra lubrication. It did seem to free the bearings up quite nicely, so hopefully when the unit's put back together it's going to be a little bit quieter, and also it's not going to get as hot. Having stripped the power supply and cleaned it up, fortunately there were no reefer capacitors on the power supply boards. However, as with a lot of HP equipment of this era, there was a Schaffner mains filter. Problem with these is they also use reefer filter capacitors inside them, and they suffer from the same problem that the outer plastic casing cracks and then moisture gets into the capacitor itself and causes it to fail. And given that these are at mains voltage, when they fail it's quite spectacular. The problem is not just the smoke and the noise, the smell is terrible. So it's out with the soldering iron, we've got to take the filter off and replace it with a new one. The replacement has got spade terminals rather than solder lugs. So what I've done is made the wiring removable. Rather than soldering onto the back of the filter, I've made it so in future it can be unplugged and pulled off. I did make sure that I didn't power up the unit until I was sure that all the reefer capacitors were gone. So now that's done, we can go ahead, power the unit up and see what we find. So now it's time to power the thing up. If all goes well, we should get a sequence of flashing LEDs as the unit goes through its self-test. Then, if the self-test is successful, all the LEDs should go out and stay out. So let's power it up and see what we get. And I think that's long enough to wait. All the LEDs are out, so as far as I can tell, the unit is functional. So the next stage of the process is getting the video up and running. The output from the computer I measured to have a 60 Hz frame rate. The stated resolution is 512 pixels by 400 lines. I couldn't find any information actually in the computer documentation itself. The only thing I could find on the net was this scan from the datasheet for the monitor that ships with this particular graphic setup. As you can see, it uses standard levels for composite video with 700 millivolts positive video signals and 300 millivolt negative sync signals, with a combined horizontal and vertical sync, the two being distinguished by the pulse width. The problem is that the scan rates are non-standard, being closer to VGA than to a composite video signal on a TV. And when I tried using the composite input on a TV, I got no success at all. I did try a GBS 8200 scan converter. These are sold for particularly converting CGA, MDA, EGA to VGA signals. It worked okay, but I found it rather noisy, which I did subsequently find was due to the power supply. But also it was trying to decode the composite signal as YUV, so it only gave me a sort of washed out white colour, which wasn't very nice to work with. So I had to investigate an alternative approach to the video signal. So what I found hunting around on the net was this circuit for a HP9000 340. I initially had tried using an off-the-shelf sync separator chip with my own design. The problem there I found was because the video signal is non-standard, I couldn't get a reliable vertical sync. and every few seconds the monitor would drop out of lock and blank the display. Building this up, I found a number of issues. It didn't work very well for me. So I worked through a few modifications. Those two components there I removed because they weren't doing anything. That was reduced to 3K. This then gave me a reasonably good detection of horizontal and vertical sync, and with that I haven't seen any problems with the display of data. When I was running this, I found that the video signal looked very much like it was running out of bandwidth. It was sharp on the rising edge and then fading out. This made me suspect that this capacitor wasn't big enough. So I raised that up all the way up to 10 microfarads using a ceramic capacitor. This appeared to work when I first powered it up, but it was giving a few problems when I ran the video test suite for the unit. So here's the test utility up and running. I'm just performing the video graphics test, and you can see here as the screen fills up with light text, it fades out. I think this is because there aren't any equalization pulses on the sync. So as the video turns more and more to white, the coupling capacitor charges up, and this ends up suppressing the video level. Obviously, this isn't a good situation, and it's going to need something done about it. I ended up doing away with this circuit altogether. What I ended up doing, and it does seem to work quite well, is removing that resistor, taking it open circuit, and then feeding this straight across into the green input to the monitor. This then relies on the 75 ohm termination in the monitor to provide this impedance. When I tested this setup, it does now seem to be working pretty well, and we've got a usable system. So here we go, booting the unit up. Powers up, the image looks quite nice. It's passed the self-test, and now it's looking for an operating system. I've paused the boot process to make sure that it doesn't auto-boot into BASIC. So, selecting the diagnostics, which is mounted in a floppy drive. Here's the test sequence. I'm running this bit in high speed because it does take a few minutes. It's doing a memory test, then it'll go through the various bits and pieces of hardware, and it ends up with a test of the graphics. Okay, here it comes. The graphics test is about to start. If you notice any changes in brightness, this is not the display on the computer, it's the auto iris on the camera attempting to compensate for the changing brightness of the screen. When you look at it, the screen looks uniform. It's not fading out like it was before. So I think we can say that we've got a successfully restored system there. If you've enjoyed this video, don't forget to like and subscribe, and please do leave me feedback in the comments. Thank you.